Hi, class. Good morning, and welcome to the continuation of our lectures in quantum mechanics. Um, Today is uh, 5th of October. Again, our main reference for this lectures is Introduction to Quantum Mechanics by David J. Griffiths. This book is nice. I have an old edition, and I recommend you to buy this book once you have the extra resources. So we discussed about infinite square wave. We discussed about harmonic oscillator, and we recently finished free particle. So infinite square wave and harmonic oscillators were solved using separation of variables, and then we um, had a non-normalizable solution for through separation of variables for the free particle, but we found out also that the free particle does not have discrete energy, but rather it involves continuous energy through the uh, continuous k variable k in the solution that we had last time. So now we look at this figure. Um, so, for example, you have this kind of potential. Looking at this one here, um, and if your object is given an energy maximum of E, for example, here, then your particle, this particle, for example, can rock from this point to this point classically. So it goes uh, back and forth between these points. So that's in classical mechanics. Um, there's also this kind of potential where in your particle, your by the way, this is called bound state. The particle is bounded. Yeah, this is a bound state. This one here, you have a particle that's going to this point, but it has only an energy up to this level. So what happens is that the particle will slide down again, goes back, and then it goes away. This one also is an example of a particle going up a potential, and then when it reaches the summit, for example, it goes down, and then it scatters, it disappears. These are examples of these potential are examples of scattering that gives scattering states of the particle. In quantum mechanics, we can also look at this example of a potential. Here you have a particle. You have a particle here. Uh, when it has just some energy E, it can rock from this point to this point, back and forth. It can do that. However, in quantum mechanics, there is a possibility that there is a probability that this particle can tunnel from this point to here, such that when it reaches here, it goes down. Because in quantum mechanics, every scenario has a probability. So this particle can be found here. It tunnels from this point to. So um, these are this is a classical bound state, but a quantum scattering state, for example, because the particle can actually tunnel from here to here. It goes down in a way. Here you have is an obvious scattering state because the particle moves along this path or along this potential. It goes up to here, and since it has no more energy to go further up, it goes back down, and then it scatters that way. This one is, of course, it has high energy, can go through the summit, and then it scatters that way. So those are scattering states and bound states. So it's a good way to distinguish which are bound states and um, scattering states. So we have two kinds of solutions to the Schrodinger equation that um, gives us bound and scattering states. So what are bound states in terms of energy? So if the energy of the particle is less than the potential energy at negative infinity at and at positive infinity, then those are bound states. Look at this one. The energy is less than the potential at infinity and less than at this side also, potential at positive infinity. So these are bound states. And for the scattering states, if the energy is greater than the potential at the infinities, so it's greater at V of negative infinity or at V at positive infinity, right here. So the energy is greater than the potential at positive infinity and at negative infinity. Those are scattering states. This one also. So this is the criterion for scattering and bound states. But in um, quantum mechanics, most potentials go to zero at infinity. So it's for bound states, you can actually say that for energy, um, for energy less than zero, it's corresponding to a bound state. And for energy greater than zero, it's corresponding to a scattering state. So I hope you can now get the distinction between a bound state and a scattering state. The potential it corresponds with, again, here and here. Bound state, scattering state, classical bound state, and quantum mechanical scattering state. So that's just an introduction to our main topic for today, which is the main topic for today, which is the direct delta function. Because we're going to solve particles constrained by a potential whose nature is a direct delta function, um, delta x, denoted by delta of x here. So anyway, delta, the direct delta function, which is actually a distribution, it's not a function because it's not defined at x equal to 0. It's infinite at x equal to 0. but it's 0 uh, for x not equal to 0. So these are the conditions of the Dirac delta function. So you have infinite for x not equal to 0, for infinite for x equal to 0, and 0 for x not equal to 0. The integral of this function or this distribution from negative infinity to positive infinity is equal to 1. The integral of delta x with respect to dx from negative infinity to positive infinity is equal to 1. By the way, you can also integrate this from a certain limit, from a certain limit from to another upper limit, provided that the argument here x is within the limit in which the delta x is an infinite. But if your but if the limit here doesn't include the argument in which the delta is not infinite, then the integral would just be 0. So it's important that the limit includes the value of the argument that makes the delta function infinite for for it to have an integral of 1. So in this case, there's a shift in the peak. For example, uh, you have a Dirac delta whose peak is at a, so the infinite value of the delta function would be at x equals a. So at x equals a, this would be delta of 0, then that has the infinite value there. So it's important that the argument, the whole argument of the delta here is 0, then that's the time you can have an infinite value of your Dirac delta. So it has some property. So if you multiply a function f of x to delta x of a, by the way, the difference between delta of x minus a and delta of x is that for this delta of x, the infinity is at x equal to 0. Here, the infinity is at x equal to a. So it has a property that if you multiply a function f of x to delta x minus a, it gives you just the same as f as the function evaluated at x equal to a times the Dirac delta function x minus a. So here you have if you integrate the function here at the left side, so here is that you integrate this will just be fa will just be constant because x now is replaced by a, so everything is a constant here. So you're just now integrating the Dirac delta of x minus a dx from negative infinity to positive infinity. This is equal to f of a. So this one is just equal to f of a. So those are the things that you have to remember for Dirac delta. So anyway, what I would tell you is that the a here, you can have a limit between a certain number to a certain upper limit, but it has to include the value of x where x is equal to a in order for you to get f of a. Otherwise, you get 0 as the integral. Now, uh, we will solve for the wave functions for a particle in a delta well, or in a Dirac delta potential well, for example. So here you have V of x equal to some alpha delta x. Um, this alpha just tells us that um, uh, it's the strength of the delta function. So uh, if you have alpha equal to 1, for example, then the integral of that will just be alpha, and it's equal to 1, for example. Um, if you have a large alpha, then the integral would also be large. So this is there's a note here. This is an artificial potential, but it is beautifully simple and in some respects closer to reality. So in this case, if your potential is this one, then your stationary state Schrödinger equation, or time-independent Schrödinger equation, will read as this. So you have negative h bar over 2m, derivative of phi, derivative of phi with respect to x squared minus alpha um, delta x times phi equals ex. So for the bound states, as we've said earlier, that is in the region x less than 0, um, V is equal to 0. The potential is equal to 0, as in the delta. If you're on the left side, of the delta, the potential there has a value 0. But at x equal to 0, Vx is infinite, negatively infinite. Because the negative is because of this sign here. So you can transform this Schrödinger equation into this, where kappa square is just equal to negative 2m over e over h bar. So look at the bound states. Let's look at the conditions of the bound state. Bound state, you have energy equal to 0. Energy equal to 0. So in this case, this is okay because you have the energy less than 0 here. So if it multiplies with negative here, it will give you positive 1. So this is kappa. This is not k, but this is kappa. So the general solution for this, one would be this one. This is the form. But now the first term, because we're looking at the region x less than 0, but at negative infinity, the negative infinity, this factor will blow up, because at negative infinity this will become positive kx, and yeah, this will go to infinite. This one at negative infinity will go to 0. So we have to eliminate this factor by setting a is equal to 0, and so that at x less than 0, we only have this wave function. For the region greater than 0, or x greater than 0, Vx is also 0. Again, V is only, or V is has only a value of infinity at x equal to 0. So the general solution would be, again, it's the same form here. It's the same as this. These are just the same. Um, but it blows up this factor, the g, this term blows up at x equal to positive infinity because this will go to infinite. So we have to set g is equal to 0 and only take f e to the kappa x for this region. So remember that for this region we accept this solution, and this for this region we accept that solution. And by the standard boundary conditions on the wave function, that phi is always continuous and the derivative phi is continuous except where the potential is infinite. So let's look at this. So our case is that for x, for so we can looking at this equation, um, for f of for phi 0, which is the boundary phi 0, this would be, this were this are supposed to be the same. This one, by continuity, by this condition, these are supposed to be the same. So uh, at x0, this would be 1, this would be 1, and so b and f should be equal, so that you can rewrite the wave function to be this one. So you can rewrite this, instead of having b and f here, you can write b and b, just that you have to um, uh, specify the regions. So here, so this is now your wave function. So let's now find b. What is b? So what is b? Let's find out. B is actually equal to square root of kappa, but we'll find that out. So now look, you have this time independent Schrodinger equation. If each term I will integrate, here, the first term I integrate with from negative epsilon to positive epsilon. These are numbers. So this one could be very small. Epsilon could be really small. So you have that for the first term here. This is the first term. Then the integral of this term and the integral of this term. So here you have this. So this one here. So the integral of this, the integral of this, and the integral of this one. So here you have an integral that is, this one is equal to 0. Why? Because you have the integral of phi x, say a function, but you have a limit here that's going to 0. So therefore, this whole thing here becomes 0. So if now this is 0, you can transfer this to the other side. That becomes negative, and so the negative here the negative here will cancel with the negative of this. This becomes negative on that side, so it becomes positive. So you multiply also 2m over h bar square, and so you will have this form. This one, the integral of this one would just be, you can write uh, the second order derivative of phi with respect to x as the first order derivative with respect to x of the first order derivative of phi with respect to x. So uh, you can then write the integral of this as this one. And what is the meaning of this delta here? This is now when you evaluated this from negative e to uh, from negative epsilon to positive epsilon, where epsilon goes to zero. Where epsilon goes. So this is just, this one is just this one, the whole thing here. And this one would just be 2m over h bar square limit as limit, the limit of the integral as epsilon goes to zero of v phi x dx. But vx is equal to, v of x, I mean, is equal to um, negative alpha delta x. So what is that? Negative alpha delta x. So you change this negative alpha delta x. What is the integral? The alpha, negative alpha is a constant, so you can take that out. Negative alpha and alpha here, you can take that out of the integral. So what's left is delta x of phi x. So the integral of that is just equal to phi 0, which is uh, from the property, here. So this is, if this is phi, of x, then this should be phi of 0. So now you have um, you have this expression. So now let's look at this. Um, you have derivative of phi dx for x greater than 0. This is negative kappa e to the negative kx, kappa x, I mean. And for x less than 0, you have positive b uh, kappa e to the kappa x. This is from here. Yeah, here. If you get the derivative of phi with respect to x, this is just equal to um, k times b e to the ekx, and also for this region, this is negative b kappa e to the negative kx. So this is just that. So your um, derivative of phi with respect to dx is just equal, on the positive region is just negative b kappa, and in the negative region, or the x less than 0, your derivative of phi with respect to x is just equal to bk. And if you subtract this, subtract this, if you subtract the, I mean, this one, if you subtract this from here, that would be um, negative b kappa minus b kappa. So that would be equal to this one here. So This is now equal to 2 times b kappa. So here you have um, uh, this is equal to, by the way, um, this one is equal to this one, of course. Uh, this one. What is 5 sub O? 5 sub O will just be, if you get this, 5 sub 0 would just be equal to B. So if you set x equal to 0, it's just equal to B. And here, if it's x equal to 0, it's just equal to B. So 5 sub 0, pi of 0 is equal to B. So this one, that's this one. And then, so you have this as equal to that. And so your kappa would just be equal to that value. M, which is the mass of the particle, times alpha over h bar square. And so with your E, having the definition, having this definition for E, you can get the energy to be uh, of this form. That's the energy. So how do we get B? So we integrate, we normalize the phi, then we get the modulus of phi. So this is 2 times b square integral. We just set the integral from 0 to infinity because everything looks the same, um, as everything looks the same on the left side and on the right side. So we just multiply by 2 here. And then if we integrate this, this is just exponential of 2kx over 2k. So 2 kappa, I mean. And then we can get the integral to be this if you review your integration. And then we have this is equal to 1. So your b now would be square root of k. So that's why in this graph you have a square root of kappa here, or the kappa here, which is this one. So that's how you get the b. So now your phi of x will now be this one here. But your kappa is what? Your kappa is just equal to this. So your square root of kappa would be square root of m times alpha over h. This one here. And then e to the so anyway, your exponential, this is kappa times x. So you have that. That's why you have this. By the way, why is it um, absolute value of x here? Because the sign could change here. It's negative for x greater than 0, and it's uh, it's negative for x equal to greater than 0, and it will be um, positive for x less than 0. So here you have this solution for bound states with a particle within Dirac delta function. So this is now your wave function for that. So anyway, now let's go to the scattering states. E greater than 0 for x greater than 0, or less than 0. So we have this solution, this one. Now we have this solution here. We have this solution for this equation because we now have a negative here. In this case, in for this differential equation, we have a positive, so we choose this solution, but we have a negative here, so that our solution will now include uh, I and I here, an imaginary number here. So in this case, um, for x less than 0, none of these two will blow up because it's sinusoidal. This one is like sine cosine. None of these will blow up at the infinities. Similarly, for x greater than 0, the solution would also be of that form and none of them blow up. But at x equal to 0, so at x equal to 0, e to the 0, e to the negative 0, e to the 0, they will just be, they will just give you this expression. So f plus g is just equal to a plus b at the boundary x equal to 0. So the derivatives of this one, the derivatives with respect to x of this one, and the derivative of with respect to x of that one will just give you this one for x. This is for x equal to 0, and this is for x less than 0. So your derivative with respect to phi, uh, derivative of phi with respect to x on the positive side, or x greater than 0, this will be ik f minus g. Then for this one, you have ik a minus b. Hence, if you subtract this from here, then it will give you this one. Also, at x equal to 0 here, that's just a plus b. So your your equation now. Oh, by the way, this one here is also equal to this expression, so that this is now uh, the phi sub o would just be equal to a plus b, so that you can write f minus g. If you transform this equation, you can write this one, f minus g, to be equal to this, where the the beta here is given by this, given by that. So the f minus g is equal to a times 1 plus 2 I beta minus b times 1 minus 2 I beta. So we can now get uh, some relationships between A, B, A, B, G, and F. So anyway, looking at the scattering experiment here. So we have this potential. We have this potential here. And then we have the wave function going to the left here. In scattering experiments, for example, um, we have this kind of scenario. So we fire some particles here. Some of the particles here, as it goes to this barrier, this potential barrier, some of the particles here will go forward, and some of the particles here, because of reflection by the barrier, some particles will go this way. And of course, we call the we call this we call this wave the incident wave. This one is the incident wave. This one is the reflected wave. This one is the transmitted wave in scattering experiment. Um, we can set G equal to 0 for scattering from the left. So usually we just have a wave from here, and then some of the particles would go, or some of the waves would go this way, and some of the waves will be reflected this way, and then they scatter. And also, if if our wave is coming from this direction, then some of the waves will be reflected there, and some of the waves will go through here. But we set G is equal to 0 for scattering experiments. So if we set G is equal to 0, then we can get from here, from this one and this one, and this equation, we can get uh, the value of B by process of elimination and F. This is now the coefficient associated to the particles which go further. I mean, which are reflected. I mean here, and these are the coefficient associated to the wave function that goes to scatter on the other side here. This one is the origin. I mean the incident wave function. So we have this, and we have this. So now um, we define an R called the reflection coefficient to be the ratio of B with respect to A. And this is just equal to the ratio square of B and A. So this is just equal to beta square times 1 plus beta square. So this is just, the beta is just this expression. And for the transmission, this is just defined as the square of the ratio of F over A. So this is now the expression for T. This is called the transmission coefficient. These are the part of the wave function that goes through the barrier. This one is the part of the coefficient associated with the wave function that is reflected by the boundary or by the barrier. So if you add R and T, you will get one. You will get one. In in terms of this, in terms of this expression, you can write R and T to be. You can write R and T to be this. Yes, that's one. So there's a note here for scattering. These scattering wave functions are not normalizable, so they do not actually represent possible particle states. Therefore, normalizable linear combination of the stationary states must be formed, just as what was done for the free particle. So here, usually in scattering, you have wave packets. That's going on there. So um, in this figure, look at this. This is now a positive delta function where the delta function is going up, unlike this barrier. Um, how could the particle from here go to this one? Because the barrier here would, it would be impossible for the particle to go from here to here, because the barrier is infinite, very high. So, but again, in quantum mechanics, the particle can tunnel through this barrier, and this phenomenon is called tunneling. There's always a probability. There's always a probability that the particle will be able to pass through here. Although the probability will be very small, but there is a probability. But classically, if you have a particle here, it can't pass. It cannot pass classically. But quantum mechanically, with a very small probability, the particle from here can pass to here, or vice versa. So that's our lesson for today. And let me just uh, take a look at the finite square whale. We discussed about the infinite square whale already, but this one would be the finite square whale. Let's just describe this, and then we'll discuss this fully in the next meeting. Um, but anyway, uh, I'll just would like to go back to the bound state solution for the Dirac delta function potential. So again, you have this. If you multiply e uh, exponential to the I e times t over h bar, then you can just use this to get the time dependent wave functions. So that's these are the bound states um, for the Dirac delta potential. For the scattering states, you don't have a normalizable wave function, but you can get the transmission and reflection coefficients here. So only bound states have normalizable wave function, but scattering states for Dirac delta doesn't have normalizable wave functions. So let's now go to the finite square whale. Here you have a potential that is that is given by this. It's a potential negative V sub O for the regions negative A to A, and then you have potential 0 for um, regions greater than A. So again, we have in this problem, we have bound states and we also have scattering states. So for bound states, we have x less than A in this region. Bound states is when energy is greater than 0. And then um, on bound states is when energy is less than 0. I'm sorry. Energy is less than 0 for bound states. For scattering states, we have E greater than 0. I'm sorry for that. So for bound states in the region x less than A, the potential is 0. So your Schrodinger equation will now look like this for this region. So you will have, if you transform that, you will have this, and then you will have kappa as equal to square root of negative 2 me over h bar. So the general solution here would be this. This would be the general solution, but the first term, because you're doing the region, the negative region, so this one will blow up. So you let A equal to 0, and only this is your solution for x less than A. And it's similar for uh, x greater than A. You will only have a solution that has the term exponential raised to the negative kappa x for x greater than A for this region here. We're looking at this region first, at this region. So in the region x negative A, in the region negative A to A here, the potential is constant, negative V sub O here. The potential is constant here. That's the potential there. So our solution will look like this. Uh, Again, we use cosine and sine because we have boundary. We have boundary. Just like the infinite square wheel that we had before, we use sine and cosine. So anyway, you can transform this time independent Schrodinger equation this, into this, but with your negative L equal to this one. And so this has a solution that's this here. So C and D here are constants. And then for the region x greater than A, as I've said, this will just be containing an exponential raised to the negative kappa x. This is for x greater than A. So finally, your solution. By the way, you can this is so you can write your phi to be this one, and then you can write your for negative phi x is this will the sign here. Um, you can just actually write the sign in terms of so for example, you can uh, use um, you can only use one of the terms here, like cosine or just sine. Um, you will not lose the generality of the function. So anyway, at looking at x equals a, looking at so you can by the way, don't be confused of the sine and cosine here. You can use cosine or just sine. You can in this case, in this solution, we use just the cosine. You can use sine or because um, a cosine is an even function. I could use the cosine as an even function so that I could set uh, negative x here, and I still have the cosine. Because if I use the sine, um, if I put negative x here, the sign of the constant will change here. So I used cosine. So anyway, I can use that because of this boundary condition that the particle is bounded by this. So the sine and cosine would have equal contribution. So I can use only cosine or sine, but in this case, I use cosine. So that if I have this and then I get um, I use the boundary condition, x equal to a, looking at the region greater than a. So this is f exponential to k to negative k over a is now equal to d cosine of LA. And if you get the derivative of this will just be negative L d sine LA. The derivative of cosine is sine. And of course, you have L here. And the derivative of cosine is negative sine, I mean. And then um, by 135, we'll be able to get L uh, uh, L to be K or kappa equal to L tangent of L of A. You can, this one is for you to be able to cancel F, you divide this by this. You divide F e to the kappa A by this, or you can just set this as, set this expression to here, and then you will get this one. So you'll be able to um, get kappa. You'll be able to get kappa equal to L tangent LA. So we will now solve for the energy of the finite square wave. So the energy would be, we let z as a variable equal to LA, and z sub 0 equal to a, which this is the half of the width of the finite square wave. Z sub o equals a over h bar squared of 2mv, v of 0. So um, here, kappa square plus L square, according to this equation, according to this equation and this equation, kappa square plus L square would just be equal to this expression. So that your Ka will be uh, Z sub O square minus Z square to the 1/2. And so your tangent Z would just be this one by this equation. So you can, uh, maybe you're confused, but you can follow the solution, or you can rewrite the solution later on as you review this lecture. So now, numerically, we can graph tangent Z and this one. Tangent Z and this expression Ka here. Ka over Z square, or Z, just Z, K over Z. So the intersection here will just give you the energy of the particle of um, an infinite of a finite square well. So you have that. So these are the solution. So for a wide, deep well, in this case, your Z sub 0 is very large. The intersections occur just slightly below Zn equals n pi over 2. So the intersections here will occur at slightly below Zn n pi over 2, which is this one. The intersection will occur here at this point. And the energy would be of this expression. For shallow, narrow well, as Z sub O decreases, there are fewer and fewer bound states until finally you will, for very narrow, that's the intersection will slowly shift to this point. For narrow well, they shift to this point until when it's so narrow, um, uh, only one state is left here. Oh, let's check this. As Z decreases, there are fewer and fewer bound states until finally, for Z sub O less than 1 pi over 2 here. So if you have, if you not, it's difficult to adjust the figure. If you make the wave very narrow, you'll only have one state left. So that uh, so that For a narrow well, uh, it's hard to illustrate, but maybe we could, um, I could maybe draw this in the next meeting, um, but anyway, what's important is that there is always one bound state, no matter how narrow is the well. There's one bound state that's left. That will always be left, no matter how narrow is the well. But anyway, these are just special cases. Shallow, narrow wells are special cases, and wide, deep well are special cases. For wide, deep well, this is like the infinite square well, only that you have some constant. So for narrow well, it's like sh- um, shallow and narrow. It's you have it's like almost flat. It's like almost flat here. So if you compress this, or if you stretch this, you will have this will be almost a straight line, and this will be almost a straight line too. It will go that way. So anyway, that's a special case. But there's always one bound state for that. There's always an intersection for that case. So that's um, for the scattering state for the infinite square well would be. So anyway, let's discuss the scattering states for the infinite square well. And the scattering states would be E greater than 0. Uh, this is the condition for scattering states. To the left, Vx is equal to 0. So you will have phi x as the solution for x less than a. But inside the well, you have again um, negative v sub o, and the solution is again this one, where L is of course this expression. To the right, for x uh, for x greater than for this region, so we're doing um, energy less than 0 for the scattering. Um, we look for that. So for x for this region, you have this solution, and then for the other side, you have this solution. We set g always to be 0, like here. So we don't consider g anymore, like here. We set g is equal to 0, so this one will not exist anymore. So that we'll only have a, f, and b. Again, scattering states does not permit normalizable wave function. We can only get the reflection and transmission coefficients. We can only get those things. Uh, so there are boundary conditions. So for the first one, for x, this is supposed to be negative a here, x less than negative a. So for the boundary conditions, we have a e to the ika plus b e to the I to the this is a times e to the negative ika plus b times e to the ika, and it's supposed to be equal to this one, to this one at the boundary. And also the derivative should be also continuous. So get the derivative of this one and the derivative of this one, um, the derivative of this and the derivative of this one, when evaluated at negative a, would also be continuous. So this will give you this expression. And then for positive a, you will have uh, this one to be equal to f e to the ika. And also the derivative, first derivative at positive a, also gives you this. Also gives you that. Remember that your phi, you have, this is for less than negative a. Sorry, this is x less than negative a. Um, this one is for this one is for x greater than a. So anyway, if you do the process of elimination algebraically, then you can find b and f to be of this form. Yeah, that form. And then you can find your transmission coefficient to be equal to this. And um, um, your reflection coefficient would be just be equal to b squared over uh, a. So you can put your f, the expression for f here, then you can find b squared over a to get the reflection coefficient. So again, the energies for perfect transmission would give you this energy, and this is quite a familiar energy for this. It's quite familiar for the finite and infinite square well. So anyway, since we're already past 1 hour, I'd give a review on this finite square well in the next meeting. Just a review, just to give you a flow of the solution. Um, for now, let's end the lecture, and I will just give you the link in our Molly classroom. By the way, uh, I plan to give an interaction session uh, uh, after discussing chapter 2, maybe next meeting. So see you and have a good day.